Hello, this is Jack Jackson. In this video, I'm going to go over a TI-84 program for performing hypothesis tests of proportions using hypergeometric binomial and normal distributions. So this program will help give us the best way to find p-values in these cases. The only real advantage of using a normal approximation for performing one sample hypothesis test for proportions is that there's a built-in one proportion z-test built into the TI graphing calculators and other programs. If you put the program on the following page into your TI-84, then the disadvantage is eliminated. So this program computes the true p-value from a hypergeometric distribution if the population size is known. If the population size is unknown, then the binomial approximation is the best. For comparison, the program also produces the more popular normal approximation p-value, the one produced by the one proportion z-test app on the calculator. The last p-value returned is the most accurate one. You can enter this program into the TI-84 for computing p-values for one sample hypothesis test for means. If you can make it to the UAFS campus, then you can link your TI-84 or TI-83 up directly with me, with my calculator, and I can transfer this program without you having to enter it yourself. But this is the program. It's not super short, but there it is. So I'm going to not go over every command here, but if you will go into your calculator and enter all of these commands as you see them on the screen here, then you will have this program. And we'll show you how it works here in just a minute. So what you would want to do is press pause, go through this, and work on typing this in your calculator carefully. Well, let's assume that you have done that at this point. Let's put it to use in this particular problem. So an organization consists of 50 people. We're told that 80% of them support John Jones for president of the organization. A sample of 5 of the members are asked if they support Mr. Jones, and 60% of them say they do support him. Perform a left-tailed test of hypothesis that the true proportion of Jones supporters is less than 80%. We're going to use an alpha of 0.1, 10%. Well, we run the program, and this is what it looks like when you run it, and of course you can use this to test your program, to test that you have it in correctly. So it's program purport 1. It says hypothesis test for one sample proportions, and then it asks you for the sample size, which is supposed to be 50, not 5. Let me see if we can fix that. I take that back. That is correct. It's the population size that's 50, and the sample size is 5. Okay, so this starts with the sample size, not the population size. So you type in 5. Then the number of successes in the sample is the next thing it asks for. Now we have to figure that out because they didn't tell us, right? So you have to take the proportion here and multiply by 5. So 5 times 0.6 is 3. If that wasn't a whole number, then we would have to round off to a whole number. So anyway, we type in 3. And then it asks us here, is this a left-tailed, right-tailed, or two-tailed? Now we said less than right here, so we use a left-tailed, so we choose number 1. In this case, the population size is known. If it's known, we want to use a hypergeometric, which is the better p-value. So that's what the program will do. So you choose known. Now, if it's known, then of course you have to tell it the population size, and so it asks you for that, and you type it in, which is 50. And the number of successes in the population is, well, we assume they're telling the truth, which is 80% of the 50, which is 40. So we type that in. So notice that the population size, the number of successes in the population, the sample size, and the number of successes in the sample all have to be whole numbers. Now, when we run this, it will return then the normal approximation p-value. So this is what it would return for a p-value if it were if you did this as a one proportion z test. Same thing your calculator would return for that. But a better approximation would be if we assume this is binomial, and we get this p-value, and the actual hypergeometric is the actual p-value, which is this one at the end. So the correct p-value to use is 0.258. The binomial approximation is a little different, but not too far off, 0.262. But the one proportion z-test is way off. It's 0.132. So the hypergeometric definitely is the one to do there to give you a better idea what the correct p-value is. In fact, all of these numbers, even the normal approximation, even though it was much smaller, was still above the alpha of 10%. So the same conclusion would be reached either way, but the p-value that you report is going to be much more accurate, and actually completely accurate if you do the hypergeometric. And once again, this is easy to use as the built-in program. So here's another example. See if you can do this one yourself and work this out. When you're finished, come back and press pause. Press pause now. Okay, now you're back. Notice that we have an organization consisting of 40 people. We're told that 45% of them support an increase in dues. A sample of size 6 of the members are asked if they support an increase in dues, and 33% say that they do support this increase. Perform a left-tailed test of hypothesis that the true proportion of members who support an increase in dues is less than 45% using alpha of 5%. Use my calculator program. How's this p-value compared to approximations from other techniques? Okay, hopefully you've done this yourself now. So you ran this program. The sample size was 6. The number of successes in the sample, 0.33 times 6 is not quite 2, but you can see that 33% has been rounded off. And so whatever you get there when you multiply 0.33 times 6, round it off to a whole number, so you put in 2. We're seeing if that's, of course, 33% is less than 45, so we suspect the true value is less than that, so we're going to do a left-tailed test in this case. And it says, so it says is less than right there in the question, so that's how we know it's a left-tailed test. This time the population size is known, and so we enter it in. It's going to ask us the population is, so we put that in, population size of 40. Number of successes is 18. Now see, how do we in the population? Well, that's 45% of 40. Again, that needs to be a whole number. So you might do that ahead of time. You could just put 0.45 times 40 here if you're sure it's going to be a whole number. So I would probably figure that out before you run the program. Figure out your x and your m value. So it produces the p-values. The normal approximation gives you a p-value of 0.28. The binomial approximation is 0.44. The actual value from the hypergeometric is 0.44. Any way you go, those are big p-values. Okay, and if we get that, it actually gives you a little bit more in this case that I didn't show you in the last example. It actually now goes and produces a confidence interval. Now this confidence interval is the one that would be produced by the one proportion z interval, the normal approximation. We'd say that we're 95% sure the true approximation is between 0 and 0.71, which is not, which is a pretty wide interval because the sample size is so low. And we do this with a binomial approximation. We get a confidence interval between 0 and 4 for the number of successes, actually the number in that sample. But that turns out to be a confidence level of 0.93. So if we treat this as a binomial, the probability would be 0.93 that we get the number of successes between 0 and 4, which is a proportion between 0 and 2/3, or 0.67. So the true p-value found from the hypergeometric distribution is 0.435, which is huge. So there is not enough evidence to reject the null hypothesis. And the 90% confidence interval is huge there, pretty wide, really wide, and certainly includes the hypothesized 45%. So we do not have evidence to reject their claim. Let's do another example. A Facebook post claims that 60% of all likely voters support the Democratic nominee for president. We surveyed 200 random likely voters and find that 52% of them support this candidate. Is there enough evidence at the alpha equals 0.05 level to determine that the claim in the post is inflated? Provide a 95% confidence interval for the true proportion of voters who support the candidate. So it's a test of proportions, so we want our our proportion 1 interval, our proportion 1 program. It's a hypothesis test for one sample proportions. The sample size is 200. The number of successes in the sample is 104. How do we find that? Well, that's 52% of 200. 0.52 times 200. Probably want to do that ahead of time. This is a left-tailed, so we think their claim is inflated. We think the true value is less than that. So we're going to test for alternative hypothesis of a proportion less than they claimed. That's a left-tailed test. This time the population size is unknown. Since it's large, number of likely voters for president is really big. So we're going to be fine with a binomial approximation, which is what you're going to have to use here, and that's what is used when you choose unknown. So then you give it the proportion of successes in the population according to the null hypothesis, which is 0.6, and the p-value then is returned. This is the normal approximation version, 0.010, and the better binomial approximation, which would be very close to the true hypergeometric distribution, and it's 0.013. Notice those are pretty close here. Sample size is 200, so that's both, NP and NQ are both going to be pretty large here, larger than 30. So you can expect these to be pretty close to each other. In fact, they are. It does, if you did a 1 proportion z interval on this now, this would give you an approximation here for the interval. It's always a good idea, particularly when you reject the null hypothesis, an hypothesis test, to accompany that with a confidence interval. The two together are much stronger than either one by itself. So what I encourage you to do now is, once you have this program in, is to go back to our previous examples of some one sample tests of proportions, whether we did them with the calculator approximation or whether we did them with by using the formulas and going through things more individually. See if you can use this shortcut program to go back and verify those results. Also, this will give you some more practice.